Welcome everyone to this video, the second video in our lecture series here on chapter 14, Chemical Kinetics. In the previous video, we introduced the idea of chemical kinetics and reaction rates and the rate of a given chemical reaction, or I should say the average reaction rate, right? In this video, we're going to talk about how that rate can depend on concentration. How the rate of a reaction depends on concentration is given by the rate law. Okay, so again, right, the rate of a reaction most likely will depend on the concentration of your reactant, right? Because the more stuff you have, probably the more stuff that's reacting given a period of time. And so, right, again, that rate is the change in concentration of, say, your reactant over your change in time, right, divided by its stoichiometric coefficient, right, would give you the rate of that reaction, right, the average rate. And so the rate law tells us how that average rate depends on the concentration of our reactant. Okay, so that rate law has the general form given here, that the rate of the reaction, that average rate of the reaction, right, equals the rate constant. Okay, rate constant is going to be some number, right? It's going to have to be determined through experiments and things like that, right? There's no universal rate constant. It depends on the reaction. And as we'll talk about later, it also depends on temperature. Okay? And then after the rate constant, it then just is the concentrations of your reactants, right? Depending on how many reactants you have, right? All multiplied together. Each one is raised to some power, okay? Those powers, n here, are the partial orders of the reaction, okay? And then the sum of those powers gives us the overall reaction order, okay? And this terminology will be used often, right? If I have some reaction and, you know, we'll take the example of the 2N2O5 going to 4NO2 plus O2, right? So this was from in the previous video, right? In this reaction, right, my reactant here, N2O5, right, if my rate law, right, is something K times concentration of N2O5, okay, let's say that's my rate law, right, and it has a power of 1 here, I would say the rate, right, that N2O5 has is partial order of the reaction with respect to N2O5 is 1, right? So the order of the reaction with respect to N2O5 is 1, okay? And the overall reaction order in this case is 1 because there's only one reactant, right? If I had multiple reactants, let's say I had some rate law, right, K A squared B, right? I'd say the order of the reaction with respect to A is 2, and I'd say the order of the reaction with respect to B is 1, right? The order of A is 2, order of B is 1, and the overall order for this example would be 3, okay? Right? Now, how do we determine these rate laws, right, experimentally in lab? One very common way of doing this is the method called method of initial rates, okay? So this is a technique where what you do in lab is you'll measure the rate of your reaction right as it starts, and you'll do this type of measurement for a variety of different reaction conditions, mainly a variety of different concentrations, okay? And once you do that, we can then use the data from these different experiments to determine the rate law and the rate constant, okay? And you do that by taking ratios of the rate law, right? So if I have experiment 1, okay, so if I have experiment 1, which has some rate, I'll call it R1, okay, that is going to have equal some rate constant times A. Let's say my reaction is A plus B going to C, right? And this is some n power, and then B1 to some m power, right? And for my experiment 2, I have reaction or rate 2 that I measured in lab, right? As the rate constant, then A is concentration of 2 to some n power, B some concentration of 2 to some n power, right? So A1, B1, right, is the concentration of A and B in experiment 1, right? A2, B2, right, it's concentration of A, B in those experiments, right? And if I were to take the ratio of these two rates, so if I essentially divide one from the other, okay, right? When I do this, right, if I set up my experiments in a very specific way to where, let's say, I do not change the concentration of B, right? Let's say B1 equals B2, okay? Well, these two things would then cancel with each other, and I would now be left with, right, and then K's cancel with each other. And so this simplifies down to something where I have R1 over R2 equals A1 to the n power over A2 to the n power, okay? And all of these numbers are determined, and I can figure out what n is from this equation here, okay? We'll do plenty of examples of this in class, okay? But that's essentially the approach that's used, okay? Right, when doing this, right, again, what we'll do is we'll pick two experiments, right, where in those two experiments, we want the concentrations of only one thing changing and the other stuff are going to be remaining constant, okay? And we do that in order to determine how the rate changes with the change of concentration of just one thing, right? If I want to look at how the rate depends on the concentration of A, I should leave everything else the same and just change the concentration of A, right? If I double the concentration of A and the rate doubles, right, then that would tell me that my reaction has an order of 1 with respect to A, okay? And we do this for all different reactants, okay? So if I have A and B are my only reactants, I would do this for A, and I would do this for B, okay? And if I need to solve for K, the rate constant, right, then once I know the rate law, and I actually know what the orders are with respect to each reactant, then I can just plug in any of the experiments into my rate law expression to calculate the value of K, right? Because K does not change based off of the change in concentrations, and so K will be the same no matter which reaction we look at. Yeah. And how you're thinking of this, right, is you're looking at, when you're taking these ratios, right, you're looking at how much the rate was multiplied versus how much the concentration was multiplied, right? So for example, if the concentration increases by a factor of 2, right, I double my concentration. I go from 1 molar to 2 molar, right, 5 molar to 10 molar, right, I double my concentration, right. If the rate stays the same, the order is going to be 0, okay. If the rate doubles, my order is going to be 1. If the rate quadruples, the order is going to be 2, and so on and so forth, right? And that's because what you're doing is you're comparing, right, the concentration is doubled, okay, and that equals the rate, okay. Concentration is doubled, and that's being raised to some power, and that equals the rate, right? And if the rate has doubled, then this power here has to equal 1, right? But let's say that if I have 2 to some power, right, equals 4, well, I know then this power here has to be 2, right? And because 2 squared gives me 4, okay? So this is how we would solve for these orders, right, with respect to each individual concentration, one at a time, okay? And here, same type of chart, right, but instead of if the concentration doubled, if it happened to triple in the experiment, things like that, right, this is kind of the how the order changes with the change in rate, okay. So finally, talking about these rate laws, we've talked about this rate constant K, okay. Now the units of K depend on the rate law. Okay, K does not have some just set of units that it's the same no matter what. The units of K depends on the rate law, depends on that specific reaction and that specific rate law, okay? And basically the units of K are whatever they need to be to make sure that the rate has units of molars per second, okay? Right? And so this is our general expression, right? The rate here has units of molars per second. K has some units that we're trying to figure out. And then here I have, molars to some n power and molar to some n power, right? And so the units of K basically end up being given by this, okay? So K has units, it's always inverse seconds, right? So the units of K always is 1/seconds, and then the concentration is going to be equal to minus the overall order minus 1, right? So if my overall order, right, so if my order, right, of overall reaction is say 2, okay, then the order minus 1 is going to be 1, and so my units of K is going to be m to the minus 1, s to the minus 1, okay? My order is 3, right? Then it end up being m to the minus 2, s to the minus 1, right? And so on and so forth, okay? And so that is how we would figure out the units of K, right? And that is the rate law, okay?